Hello everyone, welcome to another H2 Math Crash Course. So today we'll be looking at probability. So as always, I'll give some advice at the start, very general advice. Then I'll go through some of the content and the questions before finally giving a summary as well as some important stuff that you should memorize for this chapter. And so in terms of the general probability advice, I will focus on these four things, which is to memorize the properties of probability questions, or in other words, memorize the necessary things. Then there are some keywords as well in terms of question interpretation. Then there's also simple things that you can do, such as drawing tables, tree branches, or even if you're not sure how to do the chapter as a whole, you can still use simple logic and somehow find a way. And so the first step is about memorizing certain properties. So on the screen, this is basically most of the things that you have to memorize for this chapter. It may be a bit confusing at first, but I think once you understand and know the logic behind why these relations work hand in hand, you will then be able to understand and be able to use it anytime. Yeah, not necessary all the time, because you can always draw a Venn diagram. And when you draw the Venn diagram, it will show all these relations itself. Then in the case of mutually exclusive and independence, those are two different terms that you need to know the difference between them. And how you do it will be through the probability and formulas as shown below. But I'll go through that later in the video. Then the next part is keywords. So for probability, there are a lot of questions and some of them, they will have very funny words or whatever. So when you see certain words, they should ring alarm bells as to what you should do. So like in the case of questions that use at least or at most, it will denote the exclusion of extreme events. So in that case, you try and find a complement to get an answer. So you just get all the scenarios minus this complement, which is kind of like what you do for permutations and combinations as well. In the case of given and if, you can use conditional probability. In the case of mutually exclusive, that means that two events cannot happen simultaneously. And in the case of independence, it just means whether one outcome is not related by another. And it's very important that you know that mutually exclusive is not the same as independence, as they have their own test and their own meaning. So the next one is about drawing tables and tree branches. So there are several ways you can tackle probability questions. So two of them is a very systematic and more established way of writing your answer. So for some cases, you can draw tables where you can draw, in the case of rolling two dice, of course, the numbers on the dice are 1 to 6. So if you roll two dice, there will be about 36 different scenarios. So you will draw a 6x6 grid to show the two-dimensional nature as to how the two different scenarios will play simultaneously. But note that when you draw a table, you only really draw it in 2 dimensions. So if there are 3 different cases happening or 3 different events happening at the same time, you cannot really draw a table. Then in the case of tree branches, this is a more systematic way. So what happens is that the first scenario will happen, then the third. No, the first scenario will happen, then the second, then the third. So usually they will ask you to draw about 2 or 3 different stages of an event happening. So this is usable if there are about 2 different possibilities at each stage. And this is supposed to show the uniqueness of each stage. So unlike the dice roll, perhaps in a tree branch there will be, let's say, one dice with 4 sides, and then another dice with, let's say, 8 sides. So in that case, it's a different kind of stage. So in that case, that is when you can try and use a tree branch. And lastly, if you're not sure how to do a problem solving method, you can always try and use logic. Because probability can be a very logical subject in nature. Like you can just think, oh, if this happens, then what should happen next? So it's not always recommended, but you can fall back on a very fundamental level and try to get a few marks here and there using just simple logic alone. So this is the content which I'll be going through. So the main parts of probability is probability itself, the mutually exclusive events and independence, as well as conditional probability and problem solving techniques, of which there are 4 of them. So the first part is about probability as a very general basic level, as to what we learned in secondary school. So in terms of probability, we let S be the sample space of a random experiment, and we let A and B be any 2 events. So what happens is that the intersection of A and B is denoted by as such. And this means that both A and B will occur at the same time. So that's an intersection. In terms of a union, it just means that A can occur, B can occur, or both. But the idea is that at least one of it occurs. In terms of Venn diagram representation, When there's an intersection is when the areas of A and B overlap each other. And in the case of the union of A and B, is when the shaded area of A and B are combined together. So when we take the sum of the number of outcomes in events, A and B, such as NA plus NB, we will count the overlap twice. That's the thing. Because we take the whole A and we take the whole B, that intersection will be accounted for twice. So that's why to get the union, we will take the number of A and the number of B minus the number of A and B intersecting each other, then divide it of course by the total number of events that happen. So here are some important results that you can derive from a Venn diagram. So if A is a subset of B, basically meaning that everything that is in A is completely inside of B, then the probability of A is of course less than the probability of B. In the case of the probability of A union B, is just the probability of A plus the probability of B minus the intersection of A and B. So that's what we just said. Then in case of probability of A, it can also be seen as the sum of the probability of A intersecting B and the probability of A intersecting outside of B. So, and then another one is that the probability of anything outside of A and B together is just 1 minus the probability of the union of A and B. And this last part is about conditional probability, which I haven't touched yet. Basically, if you want to find the intersection, you just find the probability of A times the probability of B given that A has happened. So an example is that a card is drawn at random from an ordinary pack of 52 playing cards. Find the probability that the card is a 7, not a 7, or either an ace or a heart. So in this case, we know that there are 4 different types of cards in the ordinary deck. So as in there's spades, diamonds, hearts, and club. So each of them will have 1 7. So in this case, the probability of drawing a 7 is just 4 out of the 52 cards available. So 1 in 13. In case of the probability of not drawing a 7, it's just 1 minus the probability of drawing a 7 itself. So we just look at the complement. So in this case, we can just do 1 minus 4 over 52, which becomes 1 minus 1 over 13 equals 12 over 13. Then in case of drawing an ace or heart, we can just take up the probability of getting an ace, the probability of getting a heart. But because there are also some scenarios where you can get an ace of hearts, that's why you have to minus 1 more card. So finally you get 4 over 52 plus 13 over 52 minus 4 over 52 to get 16 over 52, which is 4 over 13. So that's a basic example of how to do probability. Then the next part is about mutually exclusive events. So 2 events A and B are said to be mutually exclusive if they cannot occur at the same time. So let's say event A is a die shows an even number when root runs, and event B is when a die shows an odd number when root runs. So because you only have one die, it can only show one number. And if it rolls an odd number, it cannot be an even number obviously. So in this case, as you can see from the diagram, A and B are mutually exclusive when the A and B circles are completely separate from each other. Whereas if they are together, it can no longer be said to be mutually exclusive. So this just means that the probability of A and B intersecting is essentially 0. So another example is this. A card is withdrawn from a random ordinary pack of 52 playing cards. Find the probability that the card is either a club or a diamond, and the probability it is a club or a king. And yeah, event A shows, oh, sorry, we don't need this. Anyway, so yeah, the probability that is either a club or a diamond is just the probability of a club plus probability of a diamond minus the probability that is both a club and a diamond at the same time. But since club and diamond are different cards intrinsically, it's just 30 over 52 plus 30 over 52, which equals to half. Then in case of the probability of it being a club or king, there can be a king of clubs. So when we add the 13 clubs and the 4 kings available, we will minus the king of clubs as well because it will overlap. So in that case, you finally get the answer of 4 over 13. Then next will be about conditional probability, which is given by the notation PA/B, which basically means the probability of A given that B has already happened. So in this case, let's say we are given 2 fair dice. The first die shows a score of 3, and another die, let's say, flew out the window. Now you need to find the probability that the sum of the 2 scores equals 8. The thing is that we already know that we got the first die of 3. So the only possible outcome to use a sum of A is if we get first die 3 and then the second die is 5, where out of the 6 different scenarios, there's one correct scenario. So that's why in this case, the given probability is 1 over 6, given that the first row is already settled. So yeah, this is some notation as to how you can express PA given B, and it's basically given as the intersection of A and B divided by the probability of B. And why we choose B is that it's the one on the right hand side of PA slash B. So the denominator will always be the given probability. Then on top is just the intersection of both of them. Then if you add up the probability of A given B and the probability of A outside, which isn't happening, given B, it will be equal to 1 also. So another example is that a card is played at random from an ordinary pack of the two playing cards. A is the event where a heart is chosen, and B is the event that either a king, queen, or a jack is chosen. So in this case, they ask you to find the probability of A given B and the probability of B given A. So in this case, part 1, we will find the probability of A intersecting B divided by the probability of B. Whereas for the second part, the probability of B given A, we still have the intersection at the top of the numerator, which will be probability of B intersecting A. But this time, we will divide by probability of A, which is why part 1 and part 2 are different answers. So note that PA given B is not equal to PB given A. So now on to independent events. So if either of the events A or B occurs without being affected by the other, then the two events can be said to be independent of each other. So if A and B are independent, then it means the probability of A given B has occurred is the same as probability of A, because that means that A is not affected by B at all. And since the probability of A given B is equal to probability of A intersecting B divided by probability of B, we can just have, and we also have probability of A given B equal probability of A. So that just means we can simplify it to the probability of A intersecting B is just the same as the two probabilities multiplied by each other. So notice that when we look at mutually exclusive events, the probability of the intersection was 0. But in the case of independent event, it may not always be 0. So that is the difference between mutually exclusive and independent. So yeah, two independent events A and B can occur at the same time, which may mean that sets A and B are not disjoint, so the probability may not always be 0. And the independence of two events cannot be demonstrated using a Venn diagram. So the test of independent events can only be proven mathematically based on the definition. And what this definition is this last line below, that the intersection of A and B has the same probability as the probability of A itself multiplied by the probability of B itself. So yeah, that is how we test for independent events. We can also do the probability of A given B just equals the probability of A itself, and vice versa for the probability of B. So yeah, if A and B are independent, then so are the following pair of events: A prime and B, A and B prime, and A prime and B prime. You don't necessarily need to memorize this, but you can always deduce this based off the Venn diagram as well as whatever mathematical practice you do. So an example of an independent events question is that a code consists of a digit chosen from 0 to 9, followed by a letter of the alphabet. So what's the probability that the code is 4F? So the thing is that we have 26 alphabets and 10 different digits. So of course, these two events are independent of each other, because an alphabet is just an alphabet and it cannot exactly relate to a number, and likewise a number is just intrinsically on its own. So in this case, the probability is just 1 over 26 times 1 over 10. Then another one is that a bag contains 5 white balls and 3 green balls. 2 balls are to be drawn from the bag. Find the probability that the first ball is green and the second ball is white if the balls are to be drawn with replacement. So a really good time to use our tree diagram would be this case. So the first one, we have the scenario where it's either a first green ball or a first white ball. Then afterwards, we'll find the probability that we will have a second green ball or a second white ball or a second green ball, second white ball for the other scenario, whether it's green or white as the first ball or second ball. So as we look here, we want to find the probability that we get a green ball first and then a white ball second. So in this case, we just find the probability that we get a green ball first and probability that we get a white ball second. So we follow that path. It will just be 3 over 8 times 5 over 8. So since there's replacement, we don't need to take a minus 1 at the denominator. So 3 over 8 times 5 over 8 was 15 over 64. So now on to some of the different problem solving techniques. So I would say there are mainly 4 different types of problem solving techniques. The first 3 are the popular ones, whereas permutations and combinations, it can work, but as we all know, permutations and combinations can be a bit of a tricky subject, so usually people try not to use it, and you don't always need to use it either. So on to problem solving techniques now. So the first one will be about table of outcomes. So the best situation to use table of outcomes is when there are 2 different events so that you can show the 2 dimensions of a table. So let's say this example, a fair die is shown twice. The events A, B, and C are defined as follows. A is when the total score is an odd number, B is when 6 appears on the first row, C is when the total score is 9. So find the probability in part 1 of A, B, and the intersection of A and B, and determine whether A and B are independent events. Then, part 2, they ask you to find the probability of C and the probability of C given B, and state whether B and C are independent events. So what we will do is that we will draw out a table as shows. So we have the first die going 1, 2, 3, 4, 5, 6, second one going 1, 2, 3, 4, 5, 6. Then you just add up the sum for each of the 36 boxes. This can be a bit time consuming, but it's also a very surefire way, as it's quite hard to go wrong with this. So for part 1, we just find the probability of A, which is half, probability of B, which is 1 over 6, and the probability of A and intersecting B, which in this case, you look at the numbers, you have 3 out of 36 scenarios, so in this case, you get 1 over 12. So, and when you want to do independence test, you find out when the probability of A intersecting B is equal to the probability of A and multiply by the probability of B. So in this case, those are the same value, and that's why we can conclude that the events A and B are independent. Then in the case of probability of C is equal to 4 out of the 36 outcome equal 1 over 9. Then for probability of C given B, you find the intersection of C and B, divide by probability of B, which in this case gives you 1 over 6. So since the probability of C given B don't equal to the probability of C, then it means that we cannot show that events B and C are independent of each other. So these are the 2 different ways that you can test for independence. One is finding the intersection, then the other is using the conditional probability in the second part. Then the next part is about Venn diagrams. So Venn diagrams are useful when you need to visualize how the events are interacting with each other. So this can be good if there's an intersection or union of 2 events. So example is that given the following probabilities, probability of A is 0.4, probability of B given A is 0.7, and the probability of A outside intersecting with B is 0.3. Find the probability of A intersecting B, probability of B, probability of A union B, and probability of A given B. So how we got the Venn diagram as shown is that we will take note of what we are given first. So the probability of A union B, the probability of A intersecting B, is just going to be the probability of A times the probability of B given A. So we already are given that, so we can just multiply them together. 0.4 times 0.7 equals 0.28. For part 2, they want to find probability of B. So this is just the sum of the probability of A intersecting B and anything outside of A intersecting with B also. So you add those 2 together, you get 0.58. As you start to do more parts of the question, you can then fill out more information in the Venn diagram. Because when you solve like a part 1 or part 2, it will also help you solving the rest of the parts as well. So in the case of finding the probability of A union B, the standard formula is that we take the probability of A plus the probability of B minus the intersection of A and B. So in this case, we're using our part 1 and part 2 answer. We take our 0.4 plus our 0.58 minus 0.28 equals to a 0.7. Then lastly, for probability of A given B, we find the probability that A and B happen at the same time intersecting each other, divide by the probability of B. So it's just 0.28 divided by 0.58, you get 14 over 29. And another example is, let's say there are 126 students, the ratio of students who only play football to the number of students who only play rugby is 7:3. 14 students do not play rugby or football at all, 42 students do play rugby and football at the same time, And so a student is chosen at random. Find the probability that the student only playing rugby is as such. So we try and use our Venn diagram to try and lay out all the information we have. So there are 14 that don't play. Minus that from the 126 means that we only have 112 left. And since there are 42 both playing, that means there are 70 people that only play either sport one at a time, or just once. So in this case, our 70 can be divided by the 7:3 ratio. So there will be 21 people playing rugby only, 49 people playing football only. So in this case, since we have the numbers, we can just find the final probability, which is just the 21 people that only play rugby out of the total 126, which will be equal to 1/6. And this is 126. Yeah. Then the next method is probability tree or tree diagram. So a probability tree is a more useful tool if you want to show sequential events, or events that occur in stages. So the number indicator on each branch represents the conditional probability of event, and the end node given will show all the events of the previous nodes that have occurred. So this is an example. 3 machines A, B, and C produce 50%, 30%, and 20% respectively of the total number of items in the factory. The percentage of the effective output of these machines are 3%, 4%, and 5% respectively. So find the probability that if an item is selected at random, that the item is defective. Then part 2, find the probability that given that the item is defective, find the probability that the item is produced by machine A. So for the first part, we can just take the 3 different scenarios. After we branch out the entire tree diagram, you'll find a case where you get A and it's defective, B, which is defective, C, which is defective. So you add up all these 3 different scenarios together, you should get 0.037. Then for part 2, you again fall back on our formula to get the probability that is A, given that the item is defective. So we'll find the intersection of A and D, so 0.5 times the 0.03 at the top branch, then divide by the probability that is defective. And that probability we already found in part 1. So like that, we do that, divide it, and then we will get 0.405. Then second example, is that Peter has a bag containing 6 black marbles and 3 white marbles. We take out 2 marbles at random from a bag. Find the probability that in part 1, he has taken out a black marble followed by a white marble, and then find the probability that he has taken out a black marble and a white marble. So for part 1, we lay out the diagram again. So it's just gonna be the first black times the second white. So 6/9 times 3/8 equals 1/4. Now in the case of taking out a black marble and a white marble, this can be any scenario. This can be black first, white second, or white first, black second. So you take out these two scenarios, 6/9 times 3/8 plus 3/9 times 6/8, that will equal to 1/2. Yeah. Then the next part, he now takes out 3 marbles at random from the bag. Find the probability that he has taken out 2 black marbles and 1 white marble. So again, we can have 3 different scenarios. We have the first black, second black, third white, first black, second white, third black, first white, second black, third black. So actually, you realize that because this one has no replacement, actually each scenario will have the same probability. So actually, we can take 6/9 times 5/8 for the black, then 3/7 for the white, and then just multiply by the number of relevant branches. Yes, the order may change here and there, but it just means we are moving the denominators around. And since the denominators are all going to be multiplied by each other, it doesn't make a difference anyway. So how we do is we take that 6/9 times 5/8 times 3/7 times the number of different scenarios, which in this case is like permutations and combinations. 3 factorial over 2 factorial due to the 2 identical black balls. Then we will get a final probability of 15/28. Then lastly will be permutations and combinations. So this is more useful when we want to just show the number of complete scenarios. So if you want a more like quantitative answer, where you want the actual hard number of how many scenarios can occur, and then just do a final divide by total number of outcomes, this is a better solving method. Although it can also be quite tedious depending on how good your permutations and combinations are. So an example of using permutations and combinations is this example. So there are 7 sopranos, 6 altos, 3 tenors, and 4 basses. The sopranos and altos are women, and the tenors and basses are men. So at a particular rehearsal, 3 members of the choir are chosen at random to make a honey drink. Find the probability that all 3 tenors are chosen, exactly 1 base is chosen, 2 women are chosen, given that exactly 1 base is chosen, and that the chosen group contains exactly 1 tenor and 1 base, or both. So for part 1, you will just use 3 choose 3 because there can only be one scenario where all the tenors are chosen and nobody else is selected. Then for your denominator, it's just the total number of outcomes, which in this case is the total number of people in the 620 choose 3. So it will be 1 over 1140. Then in the case where exactly 1 base is chosen, we will first look at the 4 bases. So 4 choose 1. Then the remaining people, there are 16 remaining, you choose 2. So that's why 4 choose 1, 16 choose 2 is the number of possible scenarios. Then we divide again by the total number of outcomes, which is 20 choose 3. So in this case, it is 480 over 1140. Then for part 3, you want to find the probability that 2 women are chosen, given that exactly 1 base is chosen. So we let A be the event that 2 women are exactly chosen, and B be the event that exactly 1 base is chosen. So we break this down. Probability of A given B is just going to be the intersection of A and B divided by the probability of B. So it will be the probability that 2 women and exactly 1 base is chosen divided by the probability that exactly 1 base is chosen. So in this case, it will be 13 choose 2. So out of the 13 women we choose 2, and 4 choose 1 to choose the 1 base. Divide by 20 choose 3. So that's the total outcomes. Then we divide by the probability that 1 base is chosen, which is our part 2 answer. So after we do that, we will get 312 divided by 480. So that's how we get our part 3 answer. Then for part 4, find the probability that the chosen group contains exactly 1 tenor, or 1 base, or both. So we let C be the event that the chosen group contains exactly 1 tenor. So probability of C is just 3 tenors choose 1 times the remaining of the 17 people choose 2 divided by 20 choose 3, which will give 408 divided by 1140. Then the probability of C in the second B is equal to the probability that we get 1 tenor and 1 base chosen. So in that case, it will be 3 choose 1 times 4 choose 1 times 13 choose 1. So we choose 1 tenor, 1 base, and then the 13 remainder we choose 1. Divide by 20 choose 3, we get 156 over 1140. So if you want to have the probability that it contains 1 tenor or 1 base or both, it's kind of like a union. So our answer will just be the probability of C union B. So in this case, we get probability of C, probability of B, and then we minus the intersection since it will overlap. So 408 over 1140 plus 480 over 1140 minus 156 over 1140, which will equal 61 over 95. So, okay, that's mainly the content and the problem solving techniques. Now I'll go to some of the more common questions that appear. So, some questions that may appear is finding the number of samples n such that we can get a minimum probability of something. Question about envelopes. Then some question about geometric series. This is also applied to the dice rolling question last part. Then we'll just have some algebraic manipulation as well. The test of proving mutual exclusivity or independence. Then there's this kind of question where you have 3 probabilities, or 3 events put together under a single probability. Then there will be a disease testing where you have a multi-stage tree diagram. And then you have a PNC question also. So the first question, find the probability of obtaining no 6s when n dice are thrown. Find the probability of obtaining at least a 6 when n dice are thrown. And then finally, how many dice are thrown so that the probability of obtaining at least 1 6 is 0.99. So the first 2 bars are quite simple. If you want no 6 in the first n dice, it's just going to be 5 over 6. So we minus the 1 over 6 possibility of a 6. Then we just do it to the power n. Then, if we want the probability of at least 1 6 when n dice are thrown, we just take 1 minus our part 1 answer, because that will eliminate the complement. Then finally, you want a probability that obtaining at least 1 6, basically our part 2 answer, is greater than 0.99. So this is the kind of question that can be thrown quite often. They'll give you an expression in terms of n, then they will ask you to find n, so that the probability of whatever it is will be greater than a certain number. And then what you use is that you will then rearrange your inequality, bring the power n down using logarithms or lns, and then you will solve the value of n. So in this case, the value of n for being equal to log 0.01 over log 5 over 6, it just 5.26. So we will round it up to 26. If you're not sure whether it's supposed to be 25 or 26, remember that you can always use your GC to find the answer and see whether it is above 0.99 or still below 0.99. So yeah, that's how you do these kind of questions, which will become quite repetitive. Then the second question is that a man writes 5 letters, one each to A, B, C, D, E. Each letter is placed in a separate envelope and sealed. A addresses the envelope at random, one each to A, B, C, D. So part 1 is find the probability that A is in the correct envelope and the letter to B is in the incorrect envelope. Then find the probability that the letter to A is in the correct envelope given that B is in the incorrect envelope. Then for part 2, find the probability that both the letters A and B are in the incorrect envelope. So for part 1, it's just gonna be getting 105 such that A is in the correct envelope. So we have A is in the correct envelope already. So there's 4 envelopes remaining and B has to be in the correct one. So we will look at C, D, E. That is the options B. So in this case, it will be 3 over 4. So the answer for part 1 is just 3 over 20. Then for part 2, probability of A given B. So it will just be 3 over 20 divided by 4 over 5. So it's just taking inspiration from our part 2 answer. Then for part 3, this may be a bit confusing, but basically, there are only 2 scenarios. The first case is that A is in B, and because A is in B, it will inherently mean that B is not in B also. So it will be in somewhere else. So that's our first case. And when that's the case, we just need A to be in B. So that's 1 over 5. Then wherever B is, as long as A is in B, that will account for all the scenarios. So that's why you only have 1 over 5. Then the second case is that A is not in B and P is not in D. So if that's the case, then that means it's among C, D, E. So for A, you take 3 over 5 and B will be 3 over 4. So yeah, those are actually the only 2 scenarios. You may think that the scenario where A is not in A and B is in A is also a possibility. But actually, when you look at case 2 will overlap that third scenario I mentioned also. So that's why in the end, you only have 2 scenarios. Because there will be an overlap if you want to consider A is not in B and then B is in A. So yeah, that's why. And for the next question, 2 players A and B play the game by throwing a fair die alternatively until one of them throws a 6 and he wins. If A begins the game, find the probability that A wins, and part 2 will find the probability that B wins. So we let WA denote the event that A wins the game, and the probability WB that B wins the game. So in this case, if you want to get the probability of WA, we just need to know whether A will get his number 6 in his first row or second row or whatever. The thing is that they alternate between games, right? So in this case, there will always be like a 5 over 6 in between. So let's say he rolls the dice on the first try, it's 1 over 6. But if he doesn't, that means he didn't get the 6, so that's a 5 over 6. Then you let B, if A wants to win, B has to lose. So he will also get a 5 over 6. Then only on the third actual roll, A will get his number 6. So actually, I think you can repeat this on and on again. But you realize that this will create a geometric sequence. Because the way A wins is if he wins on the first row, the third row, the fifth row, seventh row, so on and so forth. And so this creates a pattern, or in other words, a geometric progression, where there's a common ratio of 5 over 6 squared. And so if that's the case, you can just use this as a sigma notation and use your APGP to eventually get 1 over 6 times the summation of 1 plus, to get the summation of 1 plus 5 over 6 squared plus 5 over 6 to power 4 plus 5 over 6 to power 6, so on and so forth, you'll get 36 over 11. So eventually your probability is going to be 6 over 11. Now, in terms of using your GC, if you're not sure how to do a sigma notation, you could also just extrapolate it on your graphing calculator. So you can manually type like 5 sets of 5 over 6 squares, and eventually you'll get a similar number to 6 over 11. Then if you're not sure, just try and use some rounding and estimation to see what's the fraction you get when you have 5 over 6 geometric progression series. But usually, if you use the sigma notation, you should still be able to get it also. Then, for the probability of B to win, it's going to be the probability of A deducted from 1. Because there are only 2 scenarios. Either A wins or B wins. Then for question 4, two players A and B regularly play each other at chess. When A has the first move in the game, the probability of A winning that game is 0.4, and the probability of B winning that game is 0.2. But when B has the first move, the probability of B winning the game is 0.3, and the probability of winning a game for A is 0.2. Any game of chess that is not won by either player ends in a draw. So part 1, they want you to find, given that A and B toss a pair coin to decide who has the first move in the game, find the probability of the game ending in a draw. Then the second part is a way to make the game more balanced and more enjoyable. A and B agree to change the procedure for deciding who has the first move in the game. So as a result of the procedure, the probability of A having the first move in any game is P. So find the value of P, which gives A and B an equal chance of winning the game. So we'll look at part 1 first. So in part 1, you can have two scenarios. It is when A wins the coin toss, the pair coin, and when B wins the coin toss or the pair coin. So in this case, we want to see half. So because coin toss is a 50-50 chance, then you times, let's say A wins the coin toss, then there's a 0.4 chance of him winning, 0.2 chance of B winning, so you minus those two cases, so 1 minus 0.4 minus 0.2, to get the probability that if A wins the coin toss, it still ends in a draw. Then your second scenario, likewise, will be half to represent the coin toss, times 1 minus 0.3 minus 0.2, or in other words, 1 minus the scenario where B wins the game, or A wins the game. So in the end, that will be 0.21. So ultimately, the probability of getting a draw overall is just a summation of the two scenarios, which will equal 0.45. Then for part 2, they give you algebra. So what you do is that you make an algebraic expression. So the probability of A going first is P, then the probability of B going first is 1 minus P. Now, to get to our final answer, we need to have the answer such that the probability of A and B winning a game is the same. And so, when you're thinking of how to do this question, you have to find a way to show that in the end, probability of A winning and the probability of B winning will be the same. So, what we are going to do is that we will let ourselves find the probability of A winning, the probability of B winning. This will be in the form of algebra, but then we will equate them to each other, such that the probability of A winning equal to the probability of B winning, and then we can solve for P from there. And so that's what we did here. And that's how we end up getting an answer of 1/3. So yeah, that's basically the thinking behind how you do this question. So there will be a lot of questions also that ask you to use algebra or whatever, but whatever algebra is, you can always find a way to solve it in some way or another. So don't be too scared when you see algebra expressions in any probability or any statistics question in general. Then the next question. Two fair dice are thrown, and events A, B, and C are defined as follows. A is when the sum of two scores are odd. B is when at least one of the two scores is greater than 4. And then C is when the two scores are equal. So fine. Find your reasons clearly in each case. Which two of the three events are mutually exclusive and independent? So the first part, you'll be making and laying down all the ground numbers. So we first just find the probability of A, probability of B, probability of C. Because after we find this, then we can work on getting things whether they are mutually exclusive or mutually independent. So we'll put that there first, and then we first find mutually exclusive. So the thing with mutually exclusive is that if you want to test it, we need to see if the probability is 0. Because if the probability of A and B intersecting, A or C intersecting, if it is 0, then you can see it's mutually exclusive because there's no common scenario. So you take probability of A and probability of B happening together. In this case, A and B happening together is 50/6, which isn't 0. So in this case, A and B are not mutually exclusive. Then we look at A and C. In this case, the probability of both happening at the same time is 0. And so, since the two scores are equal, the sum cannot be odd. That's the thinking as to why A and C cannot happen at the same time. So, A and C are therefore mutually exclusive. Then for case 3, we look at B and C. So, we again look at the different scenarios. Turns out that there are 2 scenarios out of 36 where B and C can happen simultaneously. And so therefore it's not equal to 0, and therefore we conclude that B and C are mutually exclusive. Then, in the case of finding independence, we just need to prove that probability of A and B, when we multiply by them together, is equal to the probability of the intersection of A and B. Or in that case, that's whether we tell whether it's independent or not. So for case 1, A and B, we look at the probability of A times probability of B, which in this case is half times 519. In this case, it is equal to the probability of A intersecting B. So in this case, we can see that it's independent. Then probability of A multiplied by probability of C is just 1 over 2 times 1 over 6, which equals 1 over 12. So in that case, it is not equal to the probability of A intersecting C. And okay, how we get all the probability of A intersecting B, A intersecting C, and B intersecting C? We all can just use it by observing the grid as we show in the two-dimensional table below. So if we make reference to that, we can then see whether A is equal or not. So in that case, let's find that A and C are not independent. Then in case of probability of B and C, we multiply probability of B by the probability of C. Same as the first two cases, to get 3 over 4 times 1 over 6 equals 7 over 12, which in this case is not equal to probability of B intersecting C. So in that case, A, B, and C are not independent. Yeah. Then for next question, for events A and B, it is given that probability of A is equal to 0.7, probability of B is 0.6, and probability of A given B prime is equal to 0.8. So I want you to find the probability of A intersecting B prime, probability of A union B, probability of B prime given A. Then there's the next part. For a third event C, it is given that the probability of C is 0.5. A and C are independent, so find the probability of A prime intersecting C, and then find inequality satisfied by probability of A prime intersecting B intersecting C in the form P is less than the probability, P which is less than or equal to the probability of Q. So I think personally, this is probably the hardest probability question you can get. And I think that most students cannot get this, but if you can, it will give you a really big advantage on a lot of other students as well. So we just solve the first three parts first. That is the part where you try and maximize whatever you can. So for finding the probability of A intersecting B prime, we just fall back on the formula for conditional probability because they already gave that. So the probability of A given B prime is just equal to the probability of A intersecting B prime divided by probability of B prime. So in this case, we can make probability of A intersecting B prime the subject, which will then be equal to probability of A given B prime times probability of B prime. In this case, it's just going to be probability of A given B prime times 1 minus probability of B, which will just give B prime also. So in that case, you do that, put the numbers in, then we get 0.32. Then in case of probability of A union B, if you memorize the properties or you just draw a simple Venn diagram, you will also see that the probability of A union B is the probability of B plus the probability of A intersecting anything that isn't B. So in that case, it will just be 0.32 plus 0.6 equal 0.92. Because anything that's outside of B but still intersects with A is basically everything of A except the intersection. And since probability of B has the intersection, we can then just add these two probabilities together to get our 0.92. Then in case of finding a probability of B prime given A, we are just going to take the probability of B prime intersecting A divided by probability of A, which in this case will just be 0.457. Then for part 4, finding a probability of A prime intersecting C, we just find a probability of A prime 0.3, probability of C. Since the question already said that the events are independent, A and C are independent, and so will A prime and C. So that is why we can just take our 0.3 times our 0.5 to equal 0.15 to get the answer. Now is the slightly confusing part. So for these kind of questions where you ask you to find an inequality and there's 3 different events put together in a single required probability, this is basically the step-by-step process. The answer that we want to get, or the probability in question, we will first let that be equal to x. Then we try to express the surrounding probabilities within the Venn diagram in terms of x. And then try and see the area outside of A, B, and C as a whole. Because in that case, it will be 1 minus all the probabilities in A, B, and C. And when this happens, as you can see here, it will simplify to x minus 0.07. And so in that case, we can then find what is the minimum value that x has to be, which in this case is going to be 0.07. Otherwise, the entire thing will break down and it won't exist. Then you look at the other ranges of x. So you see a 0.22 minus x, a 0.15 minus x. All these different values, you can just chart it around and just try and see and observe what x can be. So after you observe here and there, you realize that there are two maximum limits, 0.15 and 0.22. And so of course, we want to have the 0.15 because then it can account for both the scenario in B and the scenario in C. So that is how we conclude that the answer is 0.07 less than or equal to x, which is less than or equal to 0.15. This question can be rather tedious, but as I said in the last tip I mentioned, if you just focus on using simple logic and seeing how the different numbers work, you can then find a maximum and lower limit. And how you do that and eventually arrive to your conclusion is just observing. Then when you observe, then you can make your final answer, and usually it will be correct, especially for these kinds of questions. Okay, then now we are going on to question 7, which is about the tree diagram. So this is where we can use tree diagram as there are two different parts. One will be whether he's positive or not, and one is whether he has actual disease or not. So the question is, a certain disease is present in 1 in 200 of the population. In a mass screening program, a quick test for the disease is used. But the test is not totally reliable. For someone who has the disease, there is a probability of 0.9 that the test will prove positive. Whereas for someone who does not have the disease, there's a probability of 0.02 that the test will also prove positive. So for part A person is selected at random and tested. Copy and complete the tree diagram, which illustrates one application of the test. Then find the probability that the person has the disease and the test is positive. Find the probability that the test is negative. Then given that the test is positive, find the probability that the person has the disease. Then for the last part, now each person takes the test 2 times in a row. Find the probability that the person is diseased and that both tests are still positive. So you draw the tree diagram as shown below. We have the first stage, which is whether they have disease or not. Then stage 2 is whether they are positive or not. So part 1, they want to find whether it's disease and positive. So then you look at the top branch, which will be 1 over 200 times 0.9 equals 9 over 2000. For probability that's negative, it's going to be two scenarios. Whether he has the disease and tested negative, and whether he doesn't have the disease and tested negative anyway. Which in this case, we take the two probabilities, put them together, sum it up, get 0.975. And part 3, they want to see whether they get the disease and it's positive. So in this case, it will be 9 over 2000 divided by the two scenarios where they are positive. 1 over 200 times 9 over 10 plus 199 over 200 times 1 over 50 to give you 0.184. Then for the last part, where they take two tests in a row. For this part, you can draw the tree diagram from, but you don't necessarily need to. So for this part, if it's both positive, you still have the given conditional probability. So in this section, it is going to be has the disease, positive, positive. So we just apply 2 rounds of being tested positive, so 2 9 over 10s. Then we divide by the case where he is positive, and that positive is twice, so 2 9 over 10s times the 1 over 200. Then for the case where he doesn't have the disease, but he tested positive twice, it will just be our 199 over 200 times 1 over 50 times 1 over 50 again. And that will give you about 91%. So yeah, that's how you do question 7. And take note that for the first part, our disease part positive, it was 0.184. So 18%. But then when you do a second test, it becomes 91%. So that just shows personally how important it is to do multiple tests, because even one more test can increase the probability by a lot, especially in the case of big numbers or big proportions like 1 over 200 and 199 over 200 in terms of relative to each other. Then next question, a group of 15 people consists of one pair of sisters, one set of 3 brothers, and 10 other people to be arranged. The 15 people are arranged randomly in a line. So find the probability that the sisters are next to each other, find the probability that the brothers are not all next to each other, and then find the probability that either sisters are next to each other, or the brothers are next to each other, or both. And find the probability that the sisters are next to each other, given that the brothers are not all next to each other. So this is more of a permutation and combination question with a probability layer on top of it. So about finding the probability that the sisters are next to each other, we are just going to group the two sisters as one unit Then we have 13 other people, so 14 units in total. So 40 factorial divided by 50 factorial. That's how we get the first part. Then afterwards, we need to make sure we arrange the two systems as well. So that's why we multiply by extra 2 factorial to get 2 over 2. Then find the probability that all the brothers are all not next to each other. So if they are not all next to each other, we just take the component. Because this is a very extreme example. So it will be 1 minus the probability that they are all next to each other. So if they are all next to each other, we group the 3 brothers as 1 unit. Then there are 12 other people. So in total we have 13 units. 30 factorial divided by 15 factorial times 3 factorial to arrange the brothers in between. So after that, we do that. It should be not 35 or 35. It's 34 or 35. Then for the next part, so we have probability of sisters next to each other being 2 over 15. Probability that brothers are not next to each other, 34 over 35. Then for part 3, we want to find the probability that either the sisters are next to each other, or the brothers are next to each other, or both. So in this case, it's kind of like having a union. So the union can have the intersection, it can have the sisters happening, or the brothers happening. So in this case, this is why we will want to find the intersection first. Then afterwards, we can use the formula of probability sisters are together plus probability brothers are together minus the intersection. So for the first part, we find the probability that sisters are together and brothers are together. So this will just be, we will group all the sisters as 1 unit, all the brothers as 1 unit. So in that case, we will finally have 12 units in total if we count the 10 other people. So 10 people plus the union of sisters plus the union of brothers, 12 factorial, divide by 15 factorial. Then of course we have to arrange the brothers and sisters in between. So that's another 3 factorial and 2 factorial. That gives you 2 over 455. Then to get the union, which is the answer we're looking for, it's going to be 2 over 15 plus 1 over 35 minus 2 over 455. Why we have 1 over 35 is because we want the brothers to be mixed with each other. So we will minus from our part 2 answer. Then for part 4, find the probability that the sisters are next to each other given that the brothers are not all next to each other. So for this to happen, we are going to find the probability that the sisters are together and the brothers are not together. So it will be 2 over 15 minus 4 over 500 minus 4 over 455, which in this case is going to be 176 divided by 1365. So then we'll do the conditional probability. In this case, it's just going to be 176 divided by 1365 divided by our 34 over 35, which will give a final answer of 88 divided by 663. Then for the last question, this is also similar to the geometric progression I mentioned earlier. So Ash and Bill each roll a fair die once by taking alternate turns. The first person to obtain a 6 allows the other person one more roll. If the person doesn't get a 6, the game is drawn. Okay, if the other person does not get a 6, the first person is won. So Ash begins the game. So find the probability that there are 2 trees and 3 trees in the first 5 rolls of the die in the game. Then find the probability that Ash wins her first. Wait, find the probability that Ash obtains her first 6 in the game on her nth roll, and find the probability that Ash wins the game. So for part 1, it's just gonna be 1 over 6 square to represent the 2 2s, then 1 over 6 cube to represent the 3s, then we will multiply by 5 factorial over 2 factorial, 3 factorial, because we are looking at the different arrangements and permutations that can happen. In that case, it will be 5 over 3888. Part 2, F obtains the first 6 in the game on her nth roll. So what this means is that for all the turns before n, neither of them have got a 6. So here is why we have 5 over 6 and 5 over 6 represent both Ash and the other person, Billy. Ash and Bill not getting a 6. They will times 1 over 6 finally. So that's why the final answer for part 2 is just 1 over 6 times 5 over 6, 2n minus 2. And for probability for Ash to win the game, it's just gonna be the case where Ash gets the 6 on her end roll, then afterwards Bill doesn't get the 6 on his next roll. So it'll be 5 over 6. So you go into our GC, you'll find the summation from 1 to infinity to get ultimately the answer, which is 5 over 36 times 1 over 1 minus 25 over 36. Now, in your GC, of course, you don't have an infinity, but what you can do is that you can just put a really large number like 10,000 inside. so that you can get the notation for essentially infinity. If that number is still too big, just give it like 1000 and you will still be able to give a relatively accurate number. And afterwards, you will get pi or 11. So this is just a recap of the different scenarios that we went through. So we can then be finding the minimum number of samples to get a minimum probability. We can be finding what happens in a geometric series, like algebraic manipulations, proving mutual exclusivity or independence. Or in the case of finding a probability of A with B and C together, those type of questions. There will also be P and C questions, some dice rolling, as well as some tree diagram in the case of multi-stage probabilities. So some reminders is that if they actually never say there's a replacement, you will assume that there's no replacement. Then when you see keywords like at least or most, this basically denotes the exclusion of extreme events. And so think of a method of taking complements. Then in the case of dice throws, if there are only two dice, you can do things like drawing tables so as to show the two dimensions. Then for mutually exclusive and independent events, they are not related to one another and you have to do different tests separately. Mutually exclusive is if the combined probability A times B is 0. Whereas if independent, A times B is equal to the intersection of A and B. So yeah. And yeah. So another thing is if you get that really weird question with A and B and C, what you need to do is just let the probability you need be X, let it out probability in A, B, C, find expression for them. There will be a common probability which can relate the two expressions together. Then you solve X to get the upper limit. Then, but also X cannot be too small, otherwise the sum of probabilities will be greater than 1. So you get the probability of everything outside of A, B, C in terms of X to get the lower limit. Then afterwards you can just deduce the range from there. So yeah. Then lastly, this is the important things that you have to memorize for probability. This is just what different notation mean, such as conditional probability, independent events, as well as some other things here and there. If you're not sure, remember that you can always use a Venn diagram during the exam as well to illustrate all these probabilities, because all of them can be illustrated like that. So yeah, that's all I have. If you have any questions about probability or if I didn't go through this clearly enough, you can always contact me on Telegram @Turismo. So yeah, that's all I have today. Thank you for watching and hope to see you in the next video.